In the simplest situation, when you have a loss, so maybe we should imagine this more as like a car accident. If X is the loss random variable, representing, say, a monetary amount of damage to your car, for example. Monetary damages could be damage to your car, could be damage to your house, could be damage to your health. It's however much you owe based on what happened. And let's just make it specific here. Let's say X is uniform on the interval from 0 to 1,000, just to pick something specific. There's lots of different assumptions I could make about X based on the situation, different models for different situations. Maybe a better model would be an exponential model. Maybe a normal model. Let's say it's uniform. So the PDF of X is 0 when X is negative, 0 when X is bigger than 1,000, and 1 over 1,000, which is 0.001 when X is between 0 and 1,000. That would be little f sub X of little x. And again, it doesn't matter where you put the open and closed circles there. I'm not even going to bother. There's a corresponding random variable. If you've got a deductible, call it Y. That is going to be the amount the insurance company actually covers. If the deductible is $100, say, then Y, the payment random variable, how much the insurance company actually pays for your loss, is 0 if your loss is less than 100. And is something positive when X is bigger than 100. If, for example, your loss is 700, you pay the first 100, the insurance company pays 600. 700 minus 100 is what they pay. X minus 100 if X is greater than or equal to 100, say. The payment variable, random variable, is a piecewise function of the loss random variable. To be consistent with our textbook notation, in chapter 4, when they define things like expectations, general expectations, I'm thinking of page 105, this thing right here. I think I want to call this function, this piecewise function, how about capital H of X? Except capital H of capital X, because capital X is a random variable. Your insurance company, based on the deductible being 100 and based on your loss distribution, is interested in the distribution of Y. When I say X is greater than or equal to 100 here, I probably should have written it more as X is between 100 and 1,000. Now you would think, perhaps, that this must mean y also has a uniform distribution on the interval from 0 to 900, say. You would think. That's not quite right. Why? Because there's a non-zero probability that y equals 0. There's a positive probability that y equals 0. Y is not a continuous random variable. It's also not discrete. It's mixed. It's a mixed random variable. Partially discrete, partially continuous. Its PDF is difficult to describe. And in fact, I think I mostly want to just avoid describing its PDF. Its CDF is describable, but a little strange. What's its CDF? As always, the CDF is going to be the probability that the random variable is less than or equal to the given number. However, because of the nature of y being this piecewise function of x, I really should think of this CDF in a piecewise way as well, although truth be told, you always want to think of these things as piecewise, right? At least unless they're defined positively for all x. But let's be extra thorough here. The CDF will equal 0 if little y is strictly less than 0. It is going to equal 1, leave some space, a lot of space in there. It is going to equal 1 if y is strictly greater than 900. What's a little confusing is what goes in between. If y equals 0, this has a positive value. What is that positive value? Let me just do a little side calculation over here. F sub capital Y of 0. Oops. Probability that y is less than or equal to 0 turns out to equal the probability that y equals 0, which, because of how y is related to x, is the same as the probability that x is less than 100. Because y will be 0 when x is less than 100, meaning when x is between 0 and 100. It's the same as x being less than 100, which is not 0, but instead is 0.1. X is uniform. There's its PDF. 100 is right here. The probability that x is 100 is the area of that box. Base times height, 100 times 0.001 is 0.1, 1/10. This is a 0.1 if y equals 0. I actually could mix case 2 and case 3 here, but I wanted to emphasize the jump discontinuity at 0. The formula for case 3, when y is strictly between 0 and 900, I can include 900 in this, will be consistent with this equaling 0.1 when y is 0. In other words, whatever formula I put here will have a limiting value of 0.1 as y goes to 0 from the right. But there's a jump discontinuity in the CDF at 0. What formula will go there? That's another side calculation. If y is between 0 and 900, that's where I want to relate the formula. I want to relate capital Y to the formula in terms of capital X being x minus 100. So this is the same as the probability that x minus 100 is less than or equal to little y. Same as the probability that x is less than or equal to y plus 100. So I need the CDF of x, which I haven't written down yet, evaluated at y plus 100. What's the CDF of x? I haven't written its formula down. I have to integrate that function. The CDF of x, when x is between 0 and 1,000, integrate this, you're going to get 0.001x. That's the CDF of x. I need to use that down there. I need to replace x with y plus 100. So I get 0.001 times y plus 100. Or 0.001y plus 0.1. That's what goes up there. 0.001y plus 0.1, which does have a limiting value of 0.1 as y goes to 0. So yeah, I could have lapped case 2 and case 3 together, but I wanted to emphasize the jump discontinuity at 0. The graph of the CDF of y looks like this. It's 0 and y is negative. Open circle right there, for sure open circle. Closed circle at 0.1 when y equals 0, and then a line looking like this, getting up to a value of 1 when y gets up to 900, and then is 1 thereafter. Not a perfect picture. That's capital F sub capital Y of little y. It's a discontinuous function at 0. What's its PDF then? Well, the PDF in general is the derivative of the CDF. So the slope of this is 0.001. So you would think that means then the graph of the CDF, of the PDF, excuse me, should be a horizontal line, right? Like that, with a value of 0.001 when y is between 0 and 900. But wait a minute, that wouldn't have an area under it equal to 1. If it was the same graph as this, except only going up to 900 instead of 1,000, its area would be 0.9, not 1. How do I get around that difficulty? There's a way to get around it, but it's complicated. It involves something called the Dirac delta function, whose value is infinite, in this case at 0. There's like an infinite derivative at 0. What? Infinity is not a number. How do you do that? That's why we don't want to worry about it, okay? Because it's just too hard for us, all right? This class is hard enough as it is. Delta function is not really a function in the usual sense. It's something called a distribution, which is not the same meaning as distribution and probability, but I don't want to get into that. That would be too far afield. It's better to just think about it with the CDF instead of thinking about it with the PDF. But wait a minute. What about the expected value of y, the mean? Wouldn't I have to deal with the PDF then? Because to find the mean, you got to integrate the variable times the PDF, right? Ah. Well, turns out we don't have to worry about the PDF still, because of the general formula for expectation that I showed you 15 minutes ago. I'll show you again. General expectation formula, this one right here, works no matter what h of x is, as long as these conditions are hold, this integral is finite. And the little f I can use is not the CDF of y, but the CDF of x, the loss random variable, which is a nice PDF that doesn't have an infinite value anymore. The original PDF for x, that's what I can use. So let's write that down now. The expected value of y does equal a function of x, h of x, it's a piecewise function, but it's still a function. And that will be, in the abstract, the integral from minus infinity to infinity of the function h of little x times the PDF of x, f sub capital X of little x. But for our example, because f sub capital X is only positive when x is between 0 and 1,000, I only need to integrate from 0 to 1,000. I'm going to just write it as an h of x here still first. The f sub x is 1 over 1,000. That's the 0.001. But what is h of x again? H of x is this thing, which is 0 up to 100 before it becomes x minus 100. So that means this integral from 0 to 1,000 actually becomes an integral from 100 to 1,000. 100 to 1,000 of x minus 100 times the 0.001. And that's the integral to do. The x minus 100 comes from the piecewise formula right there. The fact that I can start the integral at 100 is because of the fact that h of x equals 0 when x is less than 100. So the integral from 0 to 100 is 0. Does that make sense? I mean, I could have written an integral from 0 to 100, but it would have been 0. And you don't have to do this, but it might be a little easier conceptually if you don't do a substitution. U or W or whatever you want to be x minus 100, because then that'll be, you can change the limits of integration to be 0 to 900. I didn't have to do that. In the end, you're going to get 0.0005 times 900 squared for the mean. What should that be? Should that be 450? Halfway from 0 to 900? No, 405. What, shouldn't it be 450? No, it should not be 450. Because y does not have a uniform distribution on 0 to 900. Because it's mixed, it's got the non-zero probability at 0 that occurs with probability 0.1. It's sort of weighting the mean more towards 0 because of that. That's kind of an unexpected result. What we've just discovered here for the mean of y is something that you wouldn't necessarily expect intuitively. X uniform 0 to 1,000, a mean of 500. Why is this piecewise function of x subtracting off 100? Intuitively, without being careful, you might think y is uniform on the interval from 0 to 900 and having a mean of 450. But no, because 0 occurs with positive probability, 0.1, that causes the mean to be less than 450. It's not uniform on the interval from 0 to 900. I mean, if 0 occurred with a really high probability, 0.999 say, the mean would be really close to 0. Maybe $1 or something. Okay, I think we can do this in 5 minutes. Let's try to simulate this to help us believe it. See if we can do this in 5 minutes. I'm not sure if we can. Try. Okay, well, perhaps the simplest way to do this is to not do what I was thinking of, that I'll show you on Thursday, is to do a user-defined distribution, but instead, so this is going to be x data again, but now x data is going to come from a uniform distribution on 0 to 1,000. I don't know if this is the syntax here. Okay, it looks like it worked. So there's 100 x values that are uniformly distributed between 0 and 1,000. If you made a histogram of the x data, should be fairly uniform, yeah. What's its mean? It should be close to 500. One that does get closer to 500. I'm going to do it until it's clearly close to 500. There we go. If I do a piecewise function in Mathematica like this, can I apply that function to the x data? I think I can just do this. Nope, that didn't work. Oh, well, sort of works. But not so nicely. Let's see here. No, not apply. What is the command? Map. I think that's it. Map. Yeah, that works. Okay, map. Oh, I forgot. I already forgot the syntax though. Map. Okay, there we go. See it. Map H X data. There is the corresponding payments from the insurance company. Notice there are some zeros, exactly zeros. What's the mean of the Y data? It should be closer to 405 than 450. Yeah. Simulation, good for complicated situations like on Thursday when we will look at chutes and ladders. And also for just like, I don't feel so sure about the theory. Maybe I should do a simulation and see if the theory gets confirmed. Good thing. All right, have a good day.